Hello, my name is Zoni and I'm a biomedical engineering major from the class of 2020.
Hello, my name is Tomas, and I'm a physics major from the class of 2019.
We will be working through problem number 7 from chapter 6.1 in the general chemistry workbook. You should begin by working on the problem yourself to see if you can get the answer. Pause the video now until you have completed the problem. Then we'll go over it together. Part A says to calculate the energy and frequency of a photon with a wavelength of 720 nanometers. We'll start with the wavelength first. The relationship between energy and wavelength is given by the following equation. E equals hc over lambda, where h is equal to Planck's constant, or 6.626 times 10 to the negative 34th meter squared kilogram per second. And c is the speed of light, or 3 times 10 to the 8th meters per second. First, we need to convert 720 nanometers into meters in order for the units to line up. So we will take 720 nanometers and multiply by 10 to the negative 9th meters per 1 nanometer. And we get 720 times 10 to the negative 9th meters. Now we all put this all together. We have Planck's constant, which is 6.626 times 10 to the negative 34th meters squared kilogram per second times the speed of light, 3 times 10 to the 8th meters per second. And we divide that by the wavelength, which is 720 times 10 to the negative 9th meters. And we get a value of 2.76 times 10 to the negative 19th kilogram meter squared per second squared, which is equivalent to joules. So the final answer is 2.76 times 10 to the negative 19th joules. Now let's move on to frequency. The relationship between wavelength and frequency is given by the following equation. C equals wavelength times frequency. Dividing both sides by lambda, we get frequency equals speed of light over lambda. Now let's put in the information we have. So the speed of light is 3 times 10 to the 8th meters per second divided by 720 times 10 to the negative 9th meters. And we get a final answer of 4.17 times 10 to the 14th inverse seconds, which is also equal to 4.17 times 10 to the 14th hertz. Part B says to calculate the energy of a mole of photons with the same wavelength. From part A, we know the amount of energy in one photon, which is 2.76 times 10 to the negative 19 joules per photon. To convert to moles, we're going to need to use Avogadro's number, which is 6.022 times 10 to the 23rd. A relationship we can set up is that for every mole, there are 6.022 times 10 to the 23rd photons. Using this information, we can convert joules per photon to joules per mole. We take 2.76 times 10 to the negative 19 joules per photon and multiply by 6.022 times 10 to the 23rd photons per mole. And we get a final answer of 1.66 times 10 to the 5th joules per mole.
Part C asks us to calculate the wavelength and energy of a photon given its frequency. We can solve for the wavelength using the equation C equals lambda f and multiplying each side by 1 over f to come up with lambda equals C over f. We can then plug in the values for C and F. And come up with a value for lambda of 1.67 times 10 to the negative fourth meters. To solve for energy in part C, we can use the equation E equals hf and plug in the values for Planck's constant and frequency. This gives us a value of 1.19 times 10 to the negative 21st joules. Part D asks for the wavelength and frequency of a single photon if 10 to the 20th of them have 1 joule of energy. We'll introduce the variable n as the total number of photons, and E naught as the energy of all these photons. Since there are many photons, we add a term to the original equation E equals hf of n. We simply multiply by the amount of photons because the total energy of 1 joule is the combined energy of all the photons, and all the photons have the same energy. To solve for the frequency, we can rearrange the equation by multiplying by 1 over nh on each side, which gives us F equals E over n times h. We can then plug in the values that we had for E naught, n, and h. And this gives us 1 joule over n of 10 to the 20th photons times Planck's constant. We come up with a value of frequency for 1.51 times 10 to the 13th hertz. Now that we have frequency, we use the equation C equals lambda times F and rearrange the equation by dividing by frequency on both sides, which gives us lambda equals C over F. We then plug in the values for the speed of light and frequency, and we get wavelength equals 1.99 times 10 to the negative fifth meters.